Dalton's four postulates the other day about what he said about the atom, but his model was just a dot because he knew that there was a building block making up things. So his model was just like a dot. Thomson came along, J.J. Thomson, and he discovered the electron, okay, and he did it with his cathode ray experiment. All right, so the cathode ray experiment goes with him, and there's an example of that on Schoology. And his model is called the plum pudding model. And you'll see that he made it look like the electrons were like, it's more like jello, like fruit and jello, but they were just floating around. All right? Then Ernest Rutherford came along and he discovered the protons and the nucleus. So he took Thomson's model a step further, made a nucleus, and found that there were protons. And his experiment was called the gold foil experiment. And there's an example of that on Schoology also. All right? And that's his model. So he had the nucleus, and he had the protons in the nucleus, and then he had the electrons on the outside. Then James Chadwick came along, and he discovered the neutron. All right? And so he worked with the masses of atoms and discovered that all the mass was in that nucleus, and that there was another particle other than just the proton. So Chadwick discovered the neutrons, and so his model is going to have that in there in the nucleus. And then Niels Bohr came along, and he's the first guy that actually put the electrons in orbitals, okay? And his is called the planetary model. And the reason why they call it that is because it's like, he said that electrons are orbiting the nucleus like planets orbiting the sun. And we would later on find that that's not correct, that they're actually just in regions of space, but they are in orbitals, but they're not just going in circles, they're more like popping, back and forth. But his model is actually really easy to explain things with. So we still use it today to explain stuff, but just know they're not actually just moving around the nucleus like planets orbiting the sun. All right? So de Broglie and Schrodinger are the guys that came up with the quantum model, and the quantum model is the one we use today. And basically it says that that electrons, you don't know the exact speed and location of an electron, but they're in these sublevels and orbitals, and we're going to learn about those when we get to quantum mechanics, so I don't want to confuse you now. But just trust me, they're in regions of space. It's kind of like the Jimmy Neutron looking model where it just looks like they're everywhere. All right? So this is our atomic structure history with Dalton, Thomson, Rutherford, Chadwick, and Bohr, and then de Broglie and Schrodinger. And this is what their models look like. You just have to label them. So make sure you add electrons in here because he discovered the electron. You discovered the proton and the nucleus. Make sure you put that on there. And then he discovered the neutron. All right? And Bohr was the planetary model, all right, that put them in different orbitals. All right, so that's it for the atomic orbitals. Now, as far as our critical vocabulary, our first word is atoms. And obviously with an atom, we're just talking about the particles that are in the atom. And there's electrons, okay? And electrons are they're negatively charged. They have a negative charge of -1. They have 0 mass. They actually do have a mass, but it's like 1/266 of a proton. And it's because it's so small that we say it's 0. So it technically has a mass, but we're going to say it's 0 because it's so small. And they're located in the electron cloud region around the outside of the nucleus. So the electrons, the key is negative charge, mass of 0, and located in the electron cloud. The proton has a positive charge, so we say it's a +1. Okay, it has a mass of 1, and that's an atomic mass unit, so that's what the AMU stands for. All right? And it's located in the nucleus. A neutron has no charge, so it's a neutral particle. It has a mass of 1 also, and it's also located in the nucleus. And so we call these nucleons because they're in the nucleus. So if you ever see the term nucleons, those are particles in the nucleus, and that's what that means. All right? So if we know that the protons and the neutrons are in the nucleus, and that they both have a mass of 1, and then the electrons have no mass, if I'm talking about the mass number or the atomic mass of the atom, it's important to understand that that is only made up of protons and neutrons. So when I'm saying the atomic mass of an atom, that is the number of protons plus the number of neutrons. And you're going to do that in a worksheet today too to practice. Now, if I say what is the atomic number is the number of protons. And why is that important? Because the protons define the atom. Right? So any atom that has one proton is always hydrogen. Any atom that has 4 protons is beryllium. So the protons define what the atom is. All right? So it's important to understand they define the atom. And they also don't change. The only time we're going to be changing protons is when we get to nuclear chemistry, and there's a lot of energy there. But that's the last unit that we do the whole year. So the protons will not be changing at all. What are we going to be changing? We're going to be changing electrons. Okay, so there's electrons that are in the cloud outside the nucleus. All right. How do I know how many electrons there are in an atom? Well, every atom on the periodic table is neutral. When it's neutral, that means the protons equal the electrons. So if I want to know how many electrons there are, I look at the protons. So if the atomic number gives me the protons, it's also equal to the electrons in a neutral atom. All right? Now, it's important to understand that everything on the periodic table is neutral, but it's not stable. Okay? Now, in order for an element to be stable, it has to be a noble gas. So there's only one family of stable atoms, and that's this family right here. Okay? That's the only family that's stable, and that's because they have a full outer shell of electrons. What does that mean to have a full outer shell? That means that it's completely filled up. All right? The maximum number of electrons that you can have in each energy level is 2 in the first, 8 in the second, 8 in the third, 18, 18, 32. We're never really going to go past the 4th energy level in this class. Right? But just so you know, that's the maximum number you can have, and that's what the valence electrons are in the noble gases. What is a valence electron? A valence electron is an electron in the outer shell, the outer energy level. All right? So a valence electron is an electron in the outer shell. And that's where all the chemistry is happening. Okay? The outer energy level or outer shell. So that's where all the chemistry is going to be happening. We're taking off and adding electrons in that outer energy level. So how do we know what families add and what families lose electrons? Well, you're going to see, okay, just like if I had 8, 1, 2, 3, 4, 5, 6, 7, 8, okay, and just pretend 8s are the noble gases. That's what we want to be like. Well, the first family is called the alkali metals, and it has 1 valence electron. The whole family, that's why it's the family, it has 1 valence electron, okay? And if you have 1 valence electron, is it easier to gain 7 to become like this noble gas, or lose 1 to become like that noble gas? It's easier to lose 1. If you lose 1 electron, you're going to have a +1 charge. Okay, so an example of that would be like sodium. So sodium has 11 protons, okay, and it has 11 electrons, because they are equal, right? Now, it wants to look like neon. Neon has 10 protons and 10 electrons. Its outer shell wants to look like neon. So what's it going to do? Well, sodium has 2 electrons in its first energy level, right? And then it has 8 in its second energy level, and it has 1 in its third energy level. Neon has 2 in its first, 8 in its second, and it has, remember, the max it can hold is 2 and then 8, and then it's done, so it has 10 total. Excuse me. So, for sodium to look like neon, it needs to lose an electron. Okay, so it pings it off, boom, it's gone. Gets rid of that. Now look at sodium. Sodium has 11 protons, but now it has how many electrons? 10. It has 10. So if I have 11 plus 1 charges and 10 minus 1 charges, what's my net charge going to be? +1. So that's why that family, because they're all going to do that. Every one, sodium, potassium, rubidium, they're all going to lose 1 electron to look like the noble gas, to have that same outer shell as the noble gas. And to do that, it has to lose an electron. When it loses an electron, it has one less negative, so that's why it's a +1 charge. So that whole family is going to always be +1. The next family is the alkaline earth metals. They have two. The whole family has 2 valence electrons. So it's going to be easier to gain 6 or lose 2. Lose 2. So if it loses 2, it's going to form a +2 charge. Okay? Because I know it's hard. The hard thing is, if you're losing something, why is it getting positive, right? But remember, you're losing negative charges, and it's standing up against positive charges. So if I'm beryllium, and I have 4 protons, okay, and 4 electrons, then it wants to look like helium, okay, and helium has 2 electrons. For it to do that, it has to lose 2 electrons, right? So now the new beryllium atom, okay, because remember, beryllium has 2 in its first shell, and it had 2 in its second shell. Well, it wants to look like helium, and helium is stable with 2 electrons, right? So if it loses 2, now it's going to be beryllium with 4 protons and 2 electrons. Well, if I have 4 protons and 2 electrons, what's my charge going to be? +2. Just like, so beryllium is stable as a +2 ion. Okay? Going to the next family. And we're going to practice this a lot, just so you know. The next family is the boron family. All right? And it has 3 valence electrons. Is it easier to gain 5 or lose 3? Lose 3. So the boron's family is going to have a +3 charge. Okay? Carbon's family. Now carbon, okay, is it easier to gain 4 or lose 4? It's a wash. It could go either way. So carbon's family can either be +4 or -4. And that's why carbon chemistry, there's a whole branch of it. Just organic chemistry is called carbon chemistry. There's a whole branch of chemistry just on carbon because it can combine so many different ways, because it can make different charges. All right? Then I get to nitrogen's family. Nitrogen's family has 5 valence electrons in its outer shell. So is it easier to gain 3 or lose 5?
Gain.
Gain 3. So it's going to form a negative charge. Why? Because look at nitrogen. Okay? Nitrogen has 7 protons, and its electrons equal 7, right? It wants to be like neon. Neon has 10 protons, but the electrons are also 10, right? So for nitrogen to gain 3, to look like this, okay, because its first shell, you got nitrogen, if it has 7 total, its first shell has 2, and its second shell has 5, right? It wants to look like neon. Neon has 2 in its first and 8 in its second. So for nitrogen to look like that, it has to gain 1, 2, 3. If it gains 3, then it's going to have a -3 charge, right? Because now it has 7 protons and 10 electrons, giving it a -3. All right? And so the whole family is going to, that's the great thing about chemistry, is the whole family is going to follow that trend. Oxygen's family is right here. It has 6 valence electrons. Easier to gain 2 or lose 6?
Gain.
Gain 2. If you gain 2 electrons, you become a -2 ion. The halogens, is it easier to gain 1 or lose 7?
Gain.
Gain 1. Okay, so they're going to form -1 ions. And the great thing is, that's the family right here. So this chart right here, the alkaline